In this video, we're going to talk about symmetry of equations or symmetry of graphs. So first, talking about just symmetry. The word symmetry means that two things are the same on either side of some kind of point of reflection. So there are three different kinds of symmetry we're going to talk about in graphs. There are three different places a graph can be reflected across on a coordinate grid. So the first place a graph can be reflected is across the y-axis. So in this first graph we see a parabola that looks the same on each side of that y-axis. So this is what we call y-axis symmetry. The y-axis is acting as the point of reflection here, or the line of reflection in this case. And you can see they've given some sample points on this graph. Because we are reflecting across the y-axis, the y value is staying the same for both of those points. So they have the same b value in those ordered pairs. The only thing that's changing is the sign of the x value. So in this case, that a is positive to the left of the y-axis, or sorry, to the right of the y-axis, and it's negative to the left. So this will become important later when we check for symmetry. All y-axis or all graphs that are symmetric about the y-axis can be found using these points where the y value stays the same but we change the x value, and that has to be true for a graph that is symmetric about the y-axis. Similarly, we have graphs that are symmetric about the x-axis. So now this graph has just been turned on its side, and we can see that the curve of this graph is the same on each side of the x-axis this time. So this is said to have x-axis symmetry. And similar to y-axis symmetry, this time these points still share a piece of their point in common, but this time it's the x value that they share. The x value is staying the same, so we can see they have the same a value here. But across the x-axis, now the y value is changing. Those y values are positive above the x-axis and negative below the x-axis. So we can see the only difference in the points here are the b values. So it's positive above that x-axis, negative below it. Again, this will be a way for us to check for x-axis symmetry, looking at some examples later. And then lastly, we have what we call origin symmetry. So the origin is this point in the middle of our coordinate grid at 0, 0. If a graph has origin symmetry, it is the same, or it is reflected across that origin. So we can see the same curve occurs, but diagonally from each other this time. It's not stacked on top of each other like it was with x-axis symmetry. It's not side by side the way it was in y-axis symmetry. Now that symmetry is diagonal across the origin. This is what we call origin symmetry, again reflecting across that point 0, 0. Now this time, because we are going from a curve in the first quadrant where both a and b, both x and y are positive, to a curve in the third quadrant where both x and y are negative, or both a and b are negative, this time when we check for symmetry with our ordered pairs, both the signs of x and y will change. So that is a little bit different from x-axis symmetry and y-axis symmetry, where only a sign of one of the values changed. Now both signs of both values change. It is possible that a graph does not have symmetry at all. So if we're looking at the graph for y-axis symmetry, if that parabola were shifted left or right along the x-axis, now it is no longer symmetrical about the y-axis there. Think about whatever your point of symmetry is, or line of symmetry. It's cutting the graph in half. So a parabola that sits at 0, 0, like we see here in our example, that y-axis is cutting the parabola in half. But if we shift that graph to the left, the y-axis over here is no longer cutting that parabola in half. So it is no longer symmetric about the y-axis. So we will come across some graphs that do not have any symmetry to them at all. So now we're going to go through each kind of symmetry, and we're going to talk about how we check for that symmetry. So starting with y-axis symmetry, like I mentioned before with the ordered pairs, we check to see if the equation is the same when we switch out the x values. So if we replace a positive x with a negative x, do we end up with the same equation? So they've given us a sample equation here of y equals x squared minus 4. So where we have this x here in our equation, we're going to replace that with negative x. And when we simplify this, if we still end up with the equation x squared minus 4, then this graph is symmetric about the y-axis. If it gives us a new equation different from x squared minus 4, then this graph is not symmetric about the y-axis. So let's plug negative x in. So we'll have y equals, instead of x, we're going to plug in negative x, and that's what we'll be squaring, minus 4. Now when we simplify this, negative x squared, a negative times a negative is a positive, x times x is x squared. So this is still x squared minus 4. So since this equation matches the original, then the equation y equals x squared minus 4 is symmetric about the y-axis. We can prove this the way we did just here, where we switched out the x and made it negative x, but we can also use ordered pairs to help us prove that point as well. So let's look how we would use an ordered pair to help prove that point. So they've graphed y equals x squared minus 4 for us here, and provided us with some ordered pairs on this second graph. So one of the ordered pairs we see on that graph is 3, 5. So using that same test of changing the x value from that ordered pair, and we could have chosen any of the ordered pairs on our graph. We've just chosen 3, 5 as an example. If we change the x value, so if we make it negative, when we plug negative 3 in for x and positive 5 in for y, it should give us a true statement. And again, that proves that there is symmetry about the y-axis. So let's plug those in. So I'm just going to bring it over here so that I have more space. So we're going to plug in negative 3 for x and 5 for y. So now I'll have 5 equals negative 3 squared minus 4. Negative 3 squared is a positive 9. And then 9 minus 4 is 5, so we're left with the equation 5 equals 5, which is a true statement. So since we were left with a true statement, that means this graph is symmetric about the y-axis. Graphs that are symmetric about the y-axis are also considered even functions. So as we go forward, when you start practicing and looking at some examples, you will identify both the symmetry of the function and the type of function it is. So symmetry being x-axis, y-axis, or origin symmetry, and then we'll classify it as even, odd, or neither as the type of function. So moving on, let's look at x-axis symmetry now. So opposite of y-axis symmetry, now we're going to change out the y value in our equation. So we're going to replace a positive y with a negative y. And if when we plug that in, we are left with the same equation that we started with, then our graph is symmetric about the about the x-axis this time. So let's switch out that positive y for a negative y. When we simplify this, just like last time, negative y squared, a negative times a negative is a positive, y times y is y squared. So this does become positive y squared plus 2, which is exactly the same equation that we started with. So these two equations match. So this tells us that the equation x equals y squared plus 2 is symmetric about the x-axis this time. So if when we had plugged in that negative y, it left us with a negative y squared plus 2, or if it had changed up our equation more than that, then our equation would not be symmetric about the x-axis. So just like with y-axis symmetry, we can also check x-axis symmetry with an ordered pair. So you'll see that they have graphed the equation x equals y squared plus 2 for us here. And on the second graph, they have provided some ordered pairs. We can choose any of these ordered pairs to check. We're going to use the point 6, 2 as our checkpoint. And because we are checking for x-axis symmetry, that means we are changing the y value. So we're going to plug in a negative 2 for y, but we'll keep that x value of 6 positive. All right, so we're going to have 6 equals, we're going to plug in negative 2 for y plus 2. So then negative 2 squared is a positive 4. And 4 plus 2 is 6. So we are left with the equation 6 equals 6, which is a true statement. And when we are left with a true statement, that tells us that this graph is symmetric about the x-axis. X-axis symmetry, because these are not functions, remember that a function from section 1.1, it cannot repeat x values. So we can see that this is failing the vertical line test up here on the graph. So this is not a function, so we do not consider it either even or odd. So this is neither even nor odd, simply because it is not a function. All right, so then our last kind of symmetry here is symmetry about the origin. So this is where we had our symmetry in diagonal quadrants, reflecting over that point 0, 0. So this time, if we're in diagonal quadrants, thinking about like the first and third quadrants we used as our example. In the first quadrant, x and y are both positive. In the third quadrant, x and y are both negative. So we are changing both x and y when we reflect across the origin. So we are replacing x with negative x, and we're replacing y with negative y. So we're going to be changing both variables this time to check for origin symmetry. So that y will become a negative y, so we'll have negative y equals, and then we'll have the cube root of negative x this time. All right, and now we're ready to simplify. So starting with the cube root of negative x, remember that negative sign just excuse me, represents our coefficient of negative 1. And when we take the cube root of a product, so this is really negative 1 times x inside, right? We can split this up into the cube root of negative 1 times the cube root of x. And the reason I want to do that is because we can simplify the cube root of negative 1. We can get rid of the cube root there, but the cube root of x is not going to simplify. So that cube root of negative 1, a cube root just means we're trying to figure out what number do we multiply by itself 3 times to give us negative 1. And negative 1 times negative 1 is a positive 1. And if we multiply by a negative 1 a third time, that turns it back into a negative 1. So this cube root of negative 1 is just negative 1. But the cube root of x, since that x just has an exponent of 1 on it, there's not any simplifying we can do there. So that's just going to stay the cube root of x. So we were able to simplify the cube root of negative x to be negative 1 times the cube root of x is equal to negative y. And then our final step, we do want that to be a positive y, not a negative y. So we can do that by dividing by negative 1. And when we do that, our y becomes positive. And then on the right side, we also have a negative divided by a negative, which becomes a positive. So this becomes a positive cube root of x. which again is the exact equation we started with. Those two match. So that tells us that the equation y equals the cube root of x is symmetric about the origin. So again, when you're checking for origin symmetry, you change the sign of both the x and the y. And again, we can check for origin symmetry using an ordered pair as well, which is oftentimes a lot easier than just dealing with the variables. So they have graphed the cube root of x here for us. And again, they've provided us with some ordered pairs. And we are going to use the point 8,2 as our checkpoint here. And again, we could have used any ordered pairs off of that graph. We're just choosing 8,2 for this example. So if we're checking for origin symmetry, we change the signs of both of those. So we'll be plugging in a -8 for x and a -2 for y. And if when we plug those in, we get a true statement, then our equation is symmetric about the origin. There's a little bit of a mistake here. That should not be an x equals, just y equals the cube root of x. All right, so let's plug in our x and y values. So instead of y, we're going to plug in -2. Instead of x, we'll plug in -8. So simplifying the cube root of -8, just like we did earlier, we're thinking about what number do we multiply by itself 3 times to give us -8. And 2 is a number that when we cube it, it gives us +8. So if we made it -2, -2 times -2 is 4. Multiply by a third -2, 4 times -2 gives us that -8 we have inside our cube root here. So the cube root of -8 is just -2. So we're left with a statement -2 is equal to -2, which is a true statement. So because we were checking for origin symmetry and we were left with a true statement, that means this equation is symmetric about the origin. Now origin functions, or origin symmetry, functions with origin symmetry, I should say, are functions. So these are what we call odd functions. And just a way to remember this, origin starts with O, odd starts with O, so those are the two that go together. Origin symmetry is an odd function. And then just to review, we said y-axis symmetry were even functions, and then x-axis means they are not functions, so they are neither even nor odd. Now we will come across some equations sometimes that can have multiple kinds of symmetry, just depending on how they are situated on the coordinate grid. And I do specify equations and not functions because specifically if a graph has x-axis symmetry paired with either y-axis or origin symmetry, then it is not a function. So there are common graphs. For example, we see here a circle that you'll come across a lot, especially like in pre-cal, or if you were to go into calculus or some higher level math, you'll come across circles all the time, but they are not functions. So there are equations, there are certain kinds of graph that do still have symmetry to them, they're just not functions. So we're going to use this equation of a circle, x squared plus y squared equals 25, and we're going to check to see if or what kinds of symmetry this circle has. And again, it could have multiple symmetries, it could have no symmetry. We can kind of make some guesses based off the graph that we're seeing. It looks like it's probably, if we focus on the y-axis here, we can see the same half of that circle on each side of the y-axis, so it probably has y-axis symmetry. So when we check for that, that should give us a true statement. If we focus on the x-axis, we see we have that same curve above and below the x-axis. So again, this looks like it probably has x-axis symmetry, so that's what we should expect when we check for it. And then across the origin, again, we can see that same curve on each side of the origin. So really we're expecting all three of these tests to give us true statements, because from the graph it looks like a circle does have all three kinds of symmetry. So they've given us a point off of this graph, 3, 4. So we're going to use that example point from our graph here to check for our 3 different kinds of symmetry. So with x-axis symmetry, this is when we change the y value. So we'll keep the x value the same, but we will change the y value to a -4. This is what we're going to plug in to see if our graph has x-axis symmetry. So we'll plug in 3 for x and -4 for y, and then we'll simplify. So 3 squared is 9, 4 squared is 16. So then if we simplify, 9 plus 16 gives us 25. 25 equals 25. So this tells us that because that was a true statement there, this graph does have x-axis symmetry. So then we'll check for y-axis symmetry. Across the y-axis is when we change our x value. So now we're going to change x to be -3, but we'll keep y as +4. All right, so we're going to plug in a -3 for x this time, but we're going to go back to +4, and then we'll simplify. So -3 squared is 9, 4 squared is 16, equals 25. And be careful here when you're squaring a negative. Remember, a negative times a negative is a positive. So then on the left side there, 9 plus 16 is 25. So we're left with 25 equals 25. Again, that is a true statement, so that means this graph also has y-axis symmetry. So we said yes to x, we said yes to y. Let's check for origin. Now across the origin, this is where we're changing quadrants diagonally. So both x and y are switching signs. So this will be a -3 and a -4. So we'll plug in a -3 for x and a -4 for y. But again, we're still squaring these values, and when we square a negative number, we do get a positive. So it's a +9 plus a +16. And 9 plus 16 still results in 25, so we are left with 25 equals 25, which is a true statement, which means our graph also has origin symmetry. So our graph this time was symmetric about the x-axis, the y-axis, and the origin. So this is an example where multiple symmetries show up. In this case, this is not a function, which is okay, so we're not going to classify this. With the type of function, we're just going to talk about the symmetry here. And because this circle was centered about 0, 0, this circle does have all 3 kinds of symmetry over the x-axis, over the y-axis, and over the origin. So there's just this nice little table here at the bottom of this notes page to kind of help you remember which symmetry you're looking for, how do you change your ordered pairs. And ordered pairs, I think, again, are going to be the easiest way to check for symmetry. So if we're checking for the y-axis, we switch our x values. If we check for the x-axis, we switch our y values. And actually, let me fix this. This is wrong. Here for y-axis, it says if xy, then x negative y. This should be negative x, y. For x-axis, that's where we change our y value, just change a sign. And then for origin symmetry, we change the sign of both x and y. And then remember, for type of function, y-axis is what we call an even function. Origin symmetry is what we call an odd function. And then x-axis, because that is not a function, it is neither even nor odd. So feel free to review this video, watch it as many times as you need to. There are some extra examples worked out in the notes key, just so if you want some extra practice checking for types of symmetry and identifying types of functions, check those on Canvas. And feel free to ask your teacher if you have any questions about this.